Here's a number that has no right to exist everywhere it does. It shows up in circles, obviously, but also in probability, in physics, in an infinite sum of fractions that have nothing to do with circles whatsoever. That number is pi. Today, we're computing it 6 different ways. Not because we need more digits, but because each method reveals something completely different about what pi actually is. Let's go. Number 1. Archimedes polygons, 2,300 years ago. No calculator, no decimals, just a compass and patience. Archimedes' idea: you can't measure a circle directly, but polygons are easy. Draw one inside the circle, its perimeter is a bit less than the circumference. Draw one outside, its perimeter is a bit more. You've trapped pi between 2 numbers. Now keep adding sides. The polygons squeeze in from both directions. He worked up to a 96-sided polygon by hand and got pi between 3.1408 and 3.1429. 2 decimal places with a stick. Brilliant, but slow. Number 2. The Leibniz series. Pi over 4 equals 1 minus 1 third plus 1 fifth minus 1 seventh plus ... alternating signs. Odd denominators. That's it. This is the Leibniz-Gregory series, and it is simultaneously one of the most beautiful formulas in math and one of the most useless for actually computing pi. After 10 terms, 2 decimal places. After 10,000 terms, 4. It converges agonizingly slowly. It falls out of the arctangent Taylor series, evaluated at 1, which means pi is hiding inside basic calculus. Beautiful. Impractical. A perfect setup for what's coming. Number 3. Buffon's needle. The Comte de Buffon asks, if you drop a needle on a floor with parallel lines spaced 1 needle length apart, what's the probability it crosses a line? The answer is 2 over pi. A needle. A floor. And pi falls out. The geometry involves integrating over all possible angles and positions, and the cosine integral hands u2 over pi. To estimate pi, drop needles, count crossings, divide twice the drops by the crossings. No circles, just probability and a floor. Number 4. Monte Carlo. Draw a square, inscribe a quarter circle. It covers exactly pi over 4 of the square's area. Throw random points. Hits inside the curve divided by total throws converges to pi over 4. Multiply by 4, you've got pi. 10 lines of Python, 1 million random points. It works. Convergence is slow. 100 times more points for 1 extra decimal place. But this idea, solving a deterministic problem with randomness is how modern physics and engineering simulate reality. Pi was just the first example. Number 5. Euler and the Basel problem. Hold 2 things at once. 1 plus 1 quarter plus 1 ninth plus 1 16th plus ... 1 over every perfect square, summed forever. 2. This has nothing to do with circles, and yet it equals pi squared over 6. The Bernoulli brothers spent decades on this. In 1734, Euler solved it. His method, sine of x over x, has roots at every multiple of pi. Factor it as an infinite product, expand it, and match coefficients against its Taylor series. The x squared term forces pi squared over 6 to appear. Not fully rigorous by modern standards, but correct and profound. Pi living inside a sum of whole number fractions with no geometry in sight. Number 6. Ramanujan / Chudnovsky. In 1914, Ramanujan published formulas for 1 over pi. No proofs, no derivations, just the formulas. One adds 8 correct decimal places per term. The Leibniz series needed 10,000 terms for 4. In 1987, the Chudnovsky brothers built on this. Each term delivers 14 decimal digits. It's been used to compute hundreds of trillions of digits. World records running for months on supercomputers. For the record, 39 digits is enough to calculate the circumference of the observable universe to within the width of a hydrogen atom. We compute trillions because we can. Because something in us needs to. 6 methods, polygons, a crawling series, a needle on a floor, random darts, a sum of squares, a formula that looks like a threat. They all find the same number. Pi isn't just something you measure from a circle. It's something the universe keeps arriving at, from every direction, by every road. Which method surprised you most? Leave it in the comments. I'll see you next time.